Nuclear decay, this is what we call in the real world radiation. So when we talk about radiation, things being radioactive, what that means is they're giving off certain particles of radiation. And the radiation, the nuclear decay, is caused by an unstable nucleus. So what happens if there's too many protons, not enough neutrons, if that binding power, that nuclear force, isn't strong enough to hold together the repulsive force of the protons? If that happens, it undergoes this nuclear decay. And there's 4 types of nuclear decay. So 4 different processes a nucleus can undergo in order to achieve stability. They are alpha decay, beta decay, positron emission, and electron capture. So the first one is alpha decay, and alpha is symbolized with that little fish, and you can also see it written sometimes as 4-2 alpha, and that's because an alpha particle is composed of 2 protons and 2 electrons. So the 4 means there's 4 nucleons, and the 2 means there's 2 protons. There's got to be 2 protons, 2 electrons. And if you take a glance at the periodic table, 2 protons, 2 neutrons, that's a helium particle. So another way you'll see it symbolized is like this down here, 4-2 He. That really is the exact same thing as saying an alpha particle. So when things undergo decay, we have to take into account the conservation of mass. So uranium-238, which is this little particle right here, it's going to undergo alpha decay, which means it has shot off an alpha particle. When it does that, all right, we have lost 4 nucleons. So what's going to remain in that nucleus is going to be 234 nucleons, because 4 of them went the way of the buffalo with the helium atom, and 92 protons that we started off with. If we lose 2 of them, it's going to drop down to 90. So while it's undergoing this decay, uranium-238 drops to 234, and 92 drops to 90. With the change in atomic number, we change the identity of the element. So uranium is defined as having 92 protons. If uranium loses 2 protons, it's no longer uranium. If you look on your periodic table and find element number 90, you'll find out that it is thorium. So uranium-238 undergoes alpha decay to turn into thorium-234. And then uranium-234, it might be more stable than uranium-238. It might be less stable. It might undergo its own decay to turn into something else. And in fact, I'll let you know a little secret. Thorium-234 is itself not stable, so it will also undergo some form of decay, one of the other types that we're going to talk about. And that decay will turn into something else, and then that guy will decay, and it goes through an entire process until it gets to something stable. And the second possible type of decay is the beta decay. Beta is symbolized with the beta, which is just an EMO3. Sometimes you'll see it with a 0 and -1. It has a 0 up there because it has no nucleons, and it has a -1 because it has a -1 charge. So really, all that a beta particle is an electron. It's got no nucleons, and all it has is a -1 charge. But it's not an electron that came from the electron cloud, so this isn't one of those electrons that's surrounding a nucleus. Instead, this electron comes from the nucleus, and it's actually coming from a neutron. If we think of a neutron as being composed of a positive and a negative charge, and that's what makes it neutral, so that means a neutron can decay into an electron and a proton. So what a beta decay is then, it's a neutron that loses its negative charge to leave itself with a positive charge and leaves itself as a proton. So the way we could symbolize this from within the nucleus is a neutron, which is 1 nucleon and 0 charge, turning into a proton, which is 1 nucleon with a 1 charge, and an electron, which is 0 nucleons with a -1 charge. And once again, all of this sums up to be equal because 1 equals 1 plus 0, and 0 equals 1 plus -1. An example of a beta decay. So here's iodine-131 undergoing a beta decay. So within this iodine atom, one of the neutrons within the nucleus is going to decay. It's going to eject a beta particle, which is this electron that we've drawn right there. And when it does that, it's going to form a new element. So let's do the math here. If we have 131 and we lose 0 nucleons, we are going to have remaining 131 nucleons. So that's not going to change. And if we started with 53 protons and we lose a -1, what does that mean we have left here? means we've got a 54 because one of those neutrons turned into a proton, so it's going to increase our number of protons. So with a beta decay, the atomic number does not go down like it does with the alpha decay. Instead, it goes up. And so when it goes from 53 to 54, it's no longer iodine, it is now xenon. So iodine undergoes a beta decay, one of its neutrons turns into an electron, it's shot out of the nucleus, and we're left with xenon 131. So the mass doesn't change because we're keeping that particle in there. We're keeping the mass part of it in there. All we're losing is the massless electron. On to the positron emission. So a positron is just a positive beta particle. This is going to be one of those things where you say, Mr. Jones, where did that positive charge come from and how do we wind up with that? That's physics. Don't really worry about the why with this one. Just trust me. It's a positron emission. A positron is antimatter electron, if you're curious about that. So if we think of a proton as having lots of positive and a little bit of negative in it, if it loses some of its positive and it's left with an equal amount of positive and negative, it becomes a neutron. So beta positive, or a positron particle, is a proton turning into a neutron, and then we're shooting off this little massless positive particle called a positron. So this is really like an electron. It's got the same mass as an electron, but instead of a negative charge, it has a positive charge. So let's look at fluorine-17 undergoing a positron decay. So if this occurs, we have 17 and we have 0 nucleons on that side, so that means our mass is going to stay the same. It's going to stay at 17. And if we have an atomic number of 9 and it loses +1, so it loses a positive, that means our nucleus is going to be left with a charge of 8. And so 8 protons. Because remember, this is a proton decaying into a neutron, so we're going to lose one of our protons, and that will turn this element into oxygen. Positron emission is actually really important for the medical world. It's used in what's called a PET scan. So PET stands for positron emission tomography. And this is really important that we use it to identify and locate cancer before it goes too far, or to find out where it is. And it uses positron emissions to detect where those different areas are. Really, all of the nuclear chemistry and nuclear physics plays a valuable role in the medical world. It's helped us with a lot of different diagnoses, but PET is just one of the really important ones that we use for cancer detection. And now for the last type of nuclear decay, and that is the electron capture. So with electron capture, the proton actually captures one of its own electrons from its own atom. So that electron right there will come from the electron cloud. So it's one of them that's floating around the outside of the atom. The proton will gobble it up. So it will gobble up its own electron and turn itself into a neutron, because you have a positive proton and a negative electron combining to make something neutral, so neutron. So a proton, it gobbles up its own electron, nom 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 nom, neutron. And here's what this would look like. So notice when we write this out, we no longer have the particle as a product. It is now on the reactant side because it's capturing its own electron from within the atom. So this is happening internally. So we have xenon, and it's going to be gaining 0 nucleons, and so its final product is going to have the same mass, 118, and it is gaining a negative value, so that's going to turn this 54 into a 53. And when we do that, we change the atomic number to 53. That means the new element is going to be iodine. Alright, so the last type of emission, this is strictly an emission, so this is something an atom loses, not to gain particle stability, but instead to gain energy stability. So when a nucleus undergoes decay, so it loses an alpha particle, loses a beta particle, absorbs an electron, it's still not going to be stable, and that's because the particles themselves still have a lot of energy, and that energy causes them to bounce around. We can think the particles as waves, and so those waves are flying around, and they're still moving, so they're still not quite stable. In order to lose some of that energy that's making them bounce around really, really fast, it will shoot off an electromagnetic particle called a gamma particle. A gamma particle, which we symbolize with the little Y-looking guy, has 0 mass and 0 charge. It's just energy. So So it's energy that's given off to lower the overall energy of the nucleus, of the nucleons, increasing the stability. So all radioactive decay is typically accompanied by some type of gamma emission. And that gamma is just energy that's given off to increase the stability of the nucleus itself.